Welcome to NYNJPA Weather Educational Videos. So today we're going to talk about instability. Very basic overview here. I don't want to overwhelm you with a lot of data. So we're going to break this down into several different videos. The first aspect I want you to concentrate on is what is instability. Very basic, very simple way to handle this. When temperatures are warmer than they are at the surface, that's stable. For example, in this case, we have temperatures at the surface at 10 degrees Celsius. Now, any temperatures above 10 degrees Celsius aloft, let's say at 900 millibars, is a stable atmosphere. What that basically means is that as air rises, it's limited on how far it could rise, basically, let's say up to about 950 millibars, because the parcel of air, like water vapor, for example, is warmer and heavier than the, should I say, is colder and heavier than the air above it. Now, in the case of unstable, that's when air is colder aloft, above, higher in the atmosphere. Therefore, water vapor, for example, that's at the surface is able to rise higher into the atmosphere because it's warmer and lighter. So again, very basic understanding of instability. And you can see this very nicely when you're looking at a smokestack. When the smokestack has a plume where it's kind of flat and even sinking towards the ground, that means that the parcel, the pollutant, let's say carbon, or let's say dust or soot, that's coming out of that smokestack is colder than the atmosphere around it. Therefore, it's heavier and therefore it sinks. Whereas when you see a smokestack rising up into the atmosphere, that means that the atmosphere is unstable, in which, in other words, that parcel, that piece of soot or water vapor or carbon dioxide or sulfur that's rising up into the atmosphere is warmer than the surrounding atmosphere around it. So again, repeat it one more time. When a temperature at 10 degrees Celsius at the surface, let's say water vapor, all right, we have a parcel of water vapor at 10 degrees Celsius, and that rises naturally into the atmosphere. If that parcel is warmer than the surrounding atmosphere, say it's 0 degrees Celsius or freezing at 900 millibars to 800 millibars, that parcel in the atmosphere is going to be able to rise because that parcel is warmer than the surrounding atmosphere. Now, this is called conditionally unstable. Now, what that basically means is that it's dependent on how much moisture is in the atmosphere. So, in this case, what we have, this straight line here is in the case of a dry atmosphere. And this line right here is in the case of a moist atmosphere. In between here is what's called conditionally unstable. If the atmosphere is very dry, then as this parcel is rising, it's generally stable in the atmosphere. However, when the parcel is moist, it becomes unstable. So the key aspect here to understand is this aspect right here is strongly dependent on how much moisture is in the atmosphere, and the more moisture is in the atmosphere, the better potential of this parcel being able to rise in that atmosphere at a fast rate. This next chart also shows the same idea here. This is your moist adiabatic lapse rate. This is your dry adiabatic lapse rate. Absolute instability, which means no matter how much moisture is in the atmosphere, whether a lot or a little, that parcel at the atmosphere, at the bottom of the atmosphere, at the surface, is going to rise no matter what. Usually that supports the potential for thunderstorms, for example. But in the case of absolute stability, where no matter what the atmosphere is like as far as moist or stable, it's still going to be a stable environment. Now, there's always a mistake that people assume that if the atmosphere is stable, that means it's going to be clear. Not always the case. You could have a situation where you have cold air at the surface, warm air moving over it. Now, clearly, that parcel at the surface is going to be colder than the warm air moving over that cold dome. So it's a stable atmosphere. But because you have moisture moving over a cold layer of air, it produces heavy rain. So, to understand this, this is what's called stratospheric precipitation, and then you have convective precipitation. Now here's a perfect example of what's called an inversion layer. This is a case where the lower portions of the atmosphere are very stable. You can't get much more stable than this. And when it becomes stable like this, moisture and fog, well, moisture obviously, but fog, and pollutants, that's the major thing here, gets trapped at the surface. However, right above it, you can see the temperature becomes what's called very unstable. You see, you have temperatures here at 850 millibars, much warmer than at 700 millibars. So you have this rapid unstable atmosphere here. So essentially what you have is an area of cold air and then warm air over it, and then cold air aloft. And no matter how moist it gets, this layer is still going to support a stable environment. So this right here is a key sounding to support fog or smog. This also is a sounding that would suggest the potential for fog followed by heavy rainfall if this portion of the atmosphere becomes more moist. And finally, I want to show you an example of a highly unstable atmosphere. First of all, we're going to talk about CAPE. What is CAPE? Well, to understand CAPE, you have to understand how to use a skewed T diagram. Now, the green line here, this is for moisture. This red line here, this is the actual temperature at the current time. Now, what this black line here is a forecast. Let's say you have, this is the temperature and this is a dew point at this time. And they both get lifted. What happens is that eventually as you're lifting the parcel becomes what's called saturated. Now between this point and this point, this is the actual temperature here. This is what's called sin. This right here means the atmosphere is capped. So basically what you need here is an agent to lift this parcel of air because it won't do it itself. That's where a cold front comes in. Then this section here is the difference in the forecast between this parcel rising and the actual temperature. That's called CAPE. The difference between these two lines is the amount of energy in the atmosphere. Now you might be asking, well, why is it rising and bending like this? Great question. It's a matter of using the specific data that's on the chart. What I mean by that is that you have the moist adiabats, that's the green, right here. Okay, so you take this line up until you run into a moist adiabat, and then you follow that line across. And the dry adiabats, which is this right here. So what you do here is you take those two lines, you match it up along the moist adiabat, and then that's how you get your instability in the atmosphere. It sounds more complicated than what it really is, and I'm going to do a lot of videos on this. So this is a very, very basic overview of how atmospheric instability works. But if you get this basic idea, and please, let's just go back one more time to this basic chart. If your temperature at the surface is warmer than temperatures aloft, that's unstable. If your temperatures at the surface are colder than they are aloft, that's stable. And then the difference between a dry atmosphere and a moist atmosphere could also tell you the difference on whether or not you have an unstable atmosphere or not. So in this area right here, this is dependent on whether or not the atmosphere is becoming saturated, which goes back to here, this cape. This is a case of where the atmosphere is saturated. And so you see the difference here, as opposed if the atmosphere was dry, you'd have a pretty stable atmosphere. But once it becomes moist, you have a very, very unstable atmosphere. So the difference as far as the amount of moisture in the atmosphere is very key in determining instability in most cases. That's the first video. We'll have many more over the next couple of weeks on instability and how it impacts the forecast. Have a great evening, and as always, stay safe out there.